interpretation of diffusion models using quote unquote the score function. Okay, what is a score function? For a given point x, I define a score function with respect to a particular density. Let's say I have a density qx. I look at the log of this density, this probability. It's a number. It's a probability, it's a number. Log of it is a number. And I look at the gradient of this function with respect to x. It's a function of x. I look at the gradient with respect to x, therefore it will be a vector, the same size of x. That's the definition of score. So if you hear, okay, so I'm computing the score in the context of diffusion models, this is how a score is being defined. Okay, and we can have different densities. For example, you can imagine that you have the true density of your input and you compute the score with respect to that true density function that is unknown. That will be your true score function. But you can compute the density with respect to any distribution. It gives you basically a vector field, right? So it's for every x, it's your space, high dimensional space. You have x here. The score, again, it's a vector, right? So it you can add it to your x, you can subtract it from your x, whatever. So that's going to give you a vector at that particular point x as a function of the density. It's a definition. Okay, obviously we don't have it for the true distribution, Q true. But suppose we have it. Let's say I give you the score corresponding to the true distribution. Suppose I give you score, the score function corresponding to the true distribution of data. We don't have the true distribution, therefore we don't have the score, but let's say I give you this S star of X. Okay, what would happen? My question is this question. You start with some point X and you go a little bit in the direction of your score. You maybe, again, as I mentioned, score is the same length of your X, but I'm going to add a score to my X, maybe with like some scale. So this is going to take me to a new X prime. So what do I know about X prime compared to the original X? So I take an X, an input, I go a little bit in the direction of my score. And I have another input, I have another image, I have another vector. What do I know about X prime compared to X? Higher likelihood, right? So because what is the definition of score? Again, gradient of the log likelihood with respect to like the Q true. So it is like a one step of gradient ascent. You're taking one step in the for the log likelihood function. You get x prime, so this will have higher likelihood. Obviously, with respect to what? With respect to the true distribution that we computed score with respect to. So take one example. If you had the score for the true distribution, you don't have it. If you have that score, then you can update your input. Go from x to x prime. Then maybe this gives me an idea. If I had this S star of x, the score function for the ground truth, maybe I can start with some points that is random, and I apply my score function repeatedly, and it will change my distribution. Hopefully, this will converge to my ground truth distribution. So I will start with some Gaussian distribution, say Gaussian. I will, okay, so in high dimension, Gaussian is concentrated, but maybe not the best visualization. They'll just like draw it like this. It's a Gaussian distribution, 2D. Pick a point, then follow the score. You update your point, let's say x, let's say k plus delta. It's a bad notation, but anyways, I'm going to use it to not confuse with t that we used, plus delta times the score, S star, evaluated at k. So you have xk, it's an input. You just add a little bit of score to it, you get the new point, and you just repeat it. So you have this, based on this, you will get some other distribution. For each point, I'm going to do that. And then you're going to have like, you're changing your distribution. And at the end of the day, you are going to end up with some distribution, right? So you transform your distribution at each step when you are applying your score update. Okay. Question. Would the last distribution or the end distribution converge to your true distribution if you do this? So you start with Gaussian samples, and suppose you have the score for the ground truth distribution. You don't have it in practice. Suppose you do have it. And you take these samples, you just update each of them in the direction of score a little bit. You get a new distribution. Then you update them a little bit, you get another distribution. Do it like, many more times with small enough delta. Like take like 2,000 steps whatsoever. The last distribution, the ending distribution that you're going to get, would it converge to the true distribution? Because you're using the score with respect to the true distribution. Yes or no? How many people think you will converge to the true distribution if you start the process by using the score for with respect to the ground truth distribution? Can you raise your hand? Okay, mostly centered in the back rows. Okay, so who thinks it won't converge to your ground truth distribution? Okay, so great, and the rest are uncommitted. Okay, so for the folks saying that it won't converge, I think you were on that camp. So what is your rationale?
You likely run into the same issues as gradient descent, and you can find yourself stuck at a local minima or maximum as you're trying to converge to that value for distribution.
Very good. So let's imagine, for an example, suppose your ground truth itself is a Gaussian distribution for now, just for an example. So here's like the way that your densities are. Like, you know, the Gaussian at the center, it has the highest density. Now let's look at the trajectory of one point in the process of updating. And I'm assuming I have this score. Like, let's say you start here. So you are going in the direction of maximizing your likelihood, right? The score will take you here. The next step, score will take you here, will take you here, you end up here for the point that you started here. But what about this point? If you start here, what happens? Again, the score, the ground truth score that you don't have, but suppose you do have it, will take you here, will take you here, will take you here, will take you here. You end up in the same point. You end up in the local maxima of your likelihood function. Therefore, the distribution that you end up with would be just the set of your local maxima of your likelihood function. If you take samples from it, basically you're taking samples from that set with some probabilities. You are not going to take samples from your underlying distribution Q3. Therefore, no help, right? That's not very useful for me. They say even if you had the ground truth score, you can't do it. Hold on a second. 2 minutes. But it turns out, this is really amazing. It turns out if you do exactly this process, but at each step, just add a tiny bit of Gaussian noise to it, you do converge to your ground truth distribution. Do the same thing, but add a tiny bit of noise at each step. Then you do converge to your ground truth distribution. Basically, take any x, add a little bit of the score with respect to ground truth distribution. This update, as we saw, it doesn't converge, but I'm going to just add a tiny bit of noise, let's say epsilon, scaled with this parameter. And this, the distribution of your, let's say, x infinity is in fact your ground truth distribution. Amazing. Small enough, sufficiently small that. This is usually called, this is based on Langevin equation or Langevin dynamics. Plus Brownian motion. The proof is not super difficult, but not easy. I'm gonna skip the proof. So the way it is inspired by physics, right? So the Langevin dynamics, the problem is you have a liquid and you put some particles in it. and you want to see how the distribution of the particles look like. So what is the dynamic? So that's how the process is being formulated. So inspired by that, you can in fact show, again, if you take some samples, initial samples, you go in the direction of your score to maximize the likelihood, minimize the energy, so I can talk about it, and add a little bit of noise to it. Eventually, you end up converging with your ground truth distribution. Okay, now there is hope, right? Before, even if you had the score for the ground truth distribution, you couldn't converge to it. But now there is hope that if you do have the score for the ground truth distribution, now I have a way to generate samples from that ground truth distribution, which really looks like your reverse process of diffusion. So far, so good. So if we have the ground truth score, if we have the ground truth score function, meaning that I have the gradient of log of my ground truth distribution, then we have a generative model. Because I can start with some samples from a normal distribution, I can follow my score and add a little bit of Gaussian noise, scale version of it at each step, and then after a few steps, I will converge to the ground truth distribution. Basically, samples that I have will be samples from that distribution. It's a generative process. Okay, but there's an obvious question here. We don't have the ground truth score function because we don't have the underlying distribution, Q, the density of the samples that we want to generate. If we had Q true, then what are we doing, right? So I could just like take samples from that distribution. Right? So it's a small problem, small in quote unquote. We don't have the ground truth or S star of X score function. Okay. It's a block, right? So it's a hurdle. So how can we deal with this problem? Question, can we estimate the ground truth score? Again, it's a vector, right? For every X, it's a vector using a neural network. It's a valid question, right? Because I don't have it. I want to be able to approximate this ground truth score, which means that I want to find, let's say, maybe a network S sub theta. Again, the output of this network is a vector. It's a vector the same size of X because it approximates the ground truth score function. Can I find the theta such that it is close enough to S star of X? Can I do that? Do you think it is possible? Maybe I'll just write this simple optimization, minimizing the quadratic loss between these two. Maybe I'll minimize over theta for some samples that I have, let's say from observed samples in my data set, I will find theta such that the score approximation is close enough to the score approximation of the ground truth distribution. Can I do it? Can I solve this optimization? Looks like a supervised quadratic optimization, right? How many? Okay, so if you think we can solve this optimization, can you raise your hand? 1%, or a couple of people. Okay, good. If you think we cannot solve this optimization, please raise your hand. Okay, a few more people. I'll ask you, okay, so why do you think we cannot solve this optimization?
Because we don't know what S star is.
Yeah, we don't have it. Right? We don't have it because in order to solve the supervised learning optimization, okay, so I want to fit my output to some vector. But what is it? I have some training samples, I have some clean images, but that's it. I mean, what is the score? What is the log? What is the gradient of the log density, log likelihood at those points? I don't have it. But even before that, so why not, if I am approximating the gradient of my log likelihood function with a network, why shouldn't I approximate the likelihood function directly with the network? It seems like we are making our lives a little bit more difficult, right? So why not this optimization? Let's say I have another set of parameters, expectation over Q0. Let's say for density, I'm going to have a density function, and I'll with the ground truth density, I'll try to minimize a loss function. Aren't these kind of equivalent? Because obviously, if I have the density, then I can compute the gradient of the log density, log likelihood. And so why are we going through the score, which is a bit of a more complicated function, right? Because density or the probability is a number, right? So here, your network needs to predict a number. What is the likelihood of this particular x? What's the number? 0.001. But the other vector, the network for the score, it has to predict the vector, the same dimension as your x. If your x has million numbers, the output should have million numbers. What is going on? So it turns out the first one is easier and doable, and the second one is harder. And the reason is because of the normalization factor. So I'll explain it why. Normalization factor basically ensures you have a valid probability model, right? So if you, let's say for the discrete case, you want the sum of the probabilities over your discrete elements to be equal to 1. That's a valid, that should be a valid probability. Like for the continuous case, the integral should be 1 to be a valid distribution. Therefore, for every point, let's say looking at the discrete case, for example, so you have a number, or for the continuous case, you get a number in terms of your density, which is normalized to make sure that the integral of your distribution is 1. The sum of the probabilities is 1. That's called the normalization. Usually that normalization constant quite challenging to estimate based on empirical samples, because you have like some samples from your distribution, right? So how would you be able to compute and estimate the normalization constant? Normalization constant quite challenging to estimate. But interestingly, the score function gets around it. It doesn't need to know the normalization constant. You can multiply every probability with some number. It doesn't change your score. And why that is the case? Okay, let's look at the ground truth score, which is this one. And let's, like this probability, let's normalize it. Let's say I have another function, q tilde of ground truth, and this is not a valid density because the integration is not summing up to 1, but I'll normalize it. Q tilde true of x. Like this can be a number, whatever number, 5, 10, 20. You're basically scaling up everything with a constant number, but to ensure that your Q true is a valid probability, then you normalize everything to have sum to 1 or integral under the curve to be 1. All right, so in this case, what happens? Log breaks these two down. Let's suppose this is like 5. It's a constant, right? So you're multiplying every probability or dividing every probability with a number. Now what happens? You get the log of q tilde true of x, this is score, minus the gradient with respect to x of log of the integral q tilde of true of x. But this guy is a constant. You're multiplying your function with some number, 5 or something. The gradient with respect to x of the constant is 0. So your score function, therefore, is invariant to scaling, to the normalization. Doesn't matter how you are, if you're assuming the sum of your probability is 1, or in another universe, the sum of your probability can be like 20 or 100. You don't care because it's just a normalization. And that's the beauty of the score function, because that normalization is extremely challenging. Not just in this context, in like graphical models, if you have worked with like probability distributions, that is like usually like the most challenging number to estimate. In some context, it is called Z, whatever. But score function gets around it. So I really don't care, right? I don't care about the normalization. I care about the direction, the gradient with respect to x. Therefore, if you are multiplying your density with some number, it's not a valid density anymore. It will, add up to maybe your probability to 20 or minus, not minus, but like whatever number, but the direction remains the same. But here is the interesting observation. If you follow the score, you end up sampling from your ground truth distribution, from your ground truth density, without estimating the normalization constant. That is why we go and try to estimate the score function, and based on the previous argument, we can generate samples from the ground truth distribution by just following the score, adding Gaussian noise at each step. Delicate point, but I hope it is clear. Okay, but still, you know, I hope that I could motivate you why estimating score is maybe is easier than estimating the actual density, but still we need to solve this optimization. And like your friend mentioned, we don't have a supervision. We don't know what is the S star, what is the ground truth score direction for some of the samples in our training. So what should we do about it? So it turns out, let's call this optimization number one. It turns out that optimization number one is equivalent to the following optimization according to this paper. In 2005, it shows that the first optimization is equivalent to minimization over theta. Again, expectation over your Q0, your data set, trace of S theta of X plus half of norm of S theta. And this optimization is often referred to as implicit score matching. Okay, so let's see what have changed compared to the original optimization. Okay. First of all, I'm not going to go through the proof. It's a bit involved, so you can look at the original paper. We do the proof, we won't be able to cover the other topics today. But let's take it for granted. The two optimizations are equivalent. Okay, so interestingly, the second optimization, in the first optimization, I needed a direct supervision. I needed to compute the score of the ground truth score for some of the training samples for supervision, that I couldn't do it. But in the second optimization, there is no ground truth score. Here, S theta of X is the network that I have, the output of the network, so that it's a norm. So here, the gradient with respect to X of S theta of X, it's a Hessian matrix. So this term is a Hessian matrix, the second order gradient, Hessian. And trace of it will, you know, give me these numbers. Again, this will be another number. So I have a scalar function of a theta, and I'm optimizing by taking samples from my X. I'm minimizing this quantity. It's amazing, right? That the two optimizations are equivalent. Okay, therefore, we have now a practical way to compute a score function. So what should I do? I'm going to have a network, whatever network architecture that you have. The output of the network is a vector here. S theta of X gives me a vector. Okay. Then I'm going to optimize the weights by minimizing this quantity. For some samples that I have in training, I look at the output norm, look at the half of it, I'll look at the Hessian. This will be computationally intensive, right? Because you are computing a huge matrix. Right? So if your input X has like million numbers, so this will be million by million, but let's say it is possible, and then you look at the trace of it. You get the number, you use that in your optimization. But remember, again, to solve the optimization over theta, you need to take another gradient of this whole thing. So it is quite computationally challenging. Even though we don't need to compute the ground truth score, it is solvable, but computationally it is very, very difficult, especially because of this Hessian term. Because again, to optimize data, you need to compute another gradient on top of it if you're doing gradient descent. Not very easy, especially compared to the previous formulation we had based on variational lower bounds, right? So we ended up with like just a simple reconstruction loss. But this is more intense. This is more challenging. I need to have a network with output of a vector, and then this Hessian term need to compute the gradient. Not easy. But then, in another paper in 2011, it was shown. Again, this optimization we can further simplify it. That is credit to this paper at 2011. What they show is that, again, I'm not going to go into the proof. You can take a look at the paper. If you look at the noisy version of your input, where epsilon is just a normal noise you're adding to your input, let's call this optimization 2. Again, 1 is the original optimization. It is equivalent to optimization 2. All of them are equivalent to optimization 3, which is minimize theta over joint distribution of x and x tilde of this quantity, s theta of x tilde minus gradient with respect to x tilde log of q x tilde given x tilde. So this paper shows I'm just going to add a little bit of Gaussian noise to my input. That's my x tilde. Then for each pair, x and x tilde, I'm going to compute this quantity, s theta of x tilde minus the score of the conditional distribution, x tilde given x. And if I solve this, I find theta, it is the same theta as like if I solve optimization 2, and it is the same theta if I solve optimization 1. All right. But what is this guy? It's the conditional density is a Gaussian density, because that's the Gaussian noise I'm adding. It's the score of a Gaussian density. What is the score of a Gaussian density? Let's look at just normal for now. It's a side note. Side note. Suppose you have a normal density as your Q. What is the score corresponding to this, which is the gradient of log of the density? What is your density? Some constant, e to the power, what? X minus, let's say the mean is 0. Divided by 2. Okay, so the constant goes away because of the derivative. So here I have log and exponential goes away. What do I get? At the end of the day, I get the gradient of this guy, which is what? Just minus x. So in Gaussian, the score is just linear with respect to x. And if you have a scalar here, that's also like linear with that scalar. So this whole thing, therefore, is just a linear function which is 1 over sigma squared of x minus x tilde. Linear function between x and x tilde. So therefore, the optimization 3 is equivalent to optimization 4, the following optimization, where you minimize theta over your samples in your training, some noise sampled from a normal distribution, 1 over half is theta of x tilde minus 1 over sigma squared x minus x tilde. I can even be a little bit fancier and define some new notations. X minus x tilde. X tilde is the noisy version of my x. Right? So x minus x tilde is the noise I'm, roughly speaking, adding to x. I'm going to define this whole thing with the just this term x minus x tilde as epsilon. Therefore, I can write the whole thing as sigma squared is theta of x tilde minus epsilon squared. And perhaps we can define this function as epsilon tilde of x tilde minus epsilon. Just rewriting these terms with some new notation. Right, so I defined x minus x tilde as epsilon. So I multiplied both sides with sigma squared. This half doesn't matter. It is scaled, scaling everything. So I get sigma squared s theta of x tilde minus epsilon. And then I'll define this term as a new function epsilon tilde of x tilde minus epsilon. So what do I have? I'm adding noise to my input. And I have a network trying to recover back that noise. Right? That's the optimization that we end up. So let me just write the whole thing, minimize over theta. I am adding for every sample in my data set, I'm sampling from normal. And with this new notation, I have this optimization. Okay, so let's look at this and compare it with the objective of DDPM. So the only element that is different is time. And we can add time to all of the analysis that we have done. I didn't add it just to keep the notations clean. You can uniformly sample your time between 0 and t. You can have this function as a function of time. Roughly speaking, same objective. You add noise, then you train a network to denoise it. But now you have a different interpretation of your denoiser. Like your denoiser, a scaled version of it is your score function. It gives you the direction to follow. And that's exactly how the generation process in diffusion model works. So you start with a normal distribution, and then for every sample, you say, okay, look, which direction I should go to maximize my likelihood. Basically, if you're denoising it, you're going in the direction that takes you to x0, then that's probably going to maximize the likelihood. That's the score direction. And then you add noise, Brownian motion a little bit to make things more interesting. And then you keep going. Okay, I'm not saying this is the interpretation of diffusion models. There might be other ways to think about this problem. But I hope that you can see a connection between the interpretation that we have from a completely different angle, from a score, from the gradient of the log likelihood function, to the denoising objective with respect to the DDPM that we covered previously. So this is called, in the literature, denoising score matching. You're basically matching scores. That's the original optimization. And based on like these reformulations of the optimization, it's based on denoising.